Hello, friends. So we are going to be looking at the second part of questions under the topic kinematics. So let's begin. So our first question says, which of the following statements is true about 0.14 c, where c is the speed of light? A, it is the boundary for classical and relativistic mechanics. B, it is the upper limit for a particle to exist. C, it is the lower limit for relativistic mechanics. And D, it is the lower limit for quantum physics. So which of these options makes sense? Like positive sense. So let's see. Okay, A, it is the boundary for classical and relativistic mechanics. Let's see why. 0.14 c, that means we're meaning 0.14 times 3.0 times 10 to the power 8. So let's see why A is actually the right answer. Okay, so it says, as an object's speed approaches 0.14 c and beyond, the effects of spatial relativity becomes more significant, and relativistic mechanics becomes necessary to accurately describe its behavior, the behavior of the object, right? This transition point highlights the boundary where classical mechanics is no longer sufficient and relativistic effects must be taken into account. So this is the reason as to why our answer A is the option. Okay, so let's move to our next question. So our second question says, a particle of mass m strikes a rigid wall perpendicular from the left with velocity v. I think this should be perpendicularly from the left with velocity v. If the collision is perfectly elastic, the total change in momentum of the body is... So let's read it over again to better understand. A particle of mass m strikes a rigid wall perpendicular from the left with velocity v. If the collision is perfectly elastic, the total change in momentum of the body is A, 2 mv to the left, B, 2 mv to the right, C, mv to the left, and D, mv to the right. So which of these answers is correct, or let me say, is the right answer, and why? Let's see. So the right answer is A, 2 mv to the left, but why? Let's see why. Okay, so there's a different view. Okay, so we have before the collision, it moves left towards right to the wall, perpendicular. Like you have the wall, it's a vertical wall, and it's coming. And after the collision, you see it moved. The object or the particle moves from right towards left. So what do we say about this? Why is it A? And we need to show these, or we need to solve it. And okay, let's see. In a perfectly elastic collision, both momentum and kinetic energy are conserved. When the particle of mass m strikes a rigid wall perpendicular from the left with velocity v, it rebounds with the same speed but in the opposite direction, rightward. Okay, so that's a statement. A statement introducing our solution and making sense of it. So let's now look at it in the solving, as in like, okay, mathematically, let's see, and yeah, physically. Okay, so we have momentum. That is okay. So we're dealing with the case before the collision, and we know that momentum is equals to the mass times the velocity, right? And here in this situation, since as it's before collision, so we're moving from left towards the right, as you can see here. So if we know that this is the mass times velocity for our momentum, and in most cases you see small m, but here the equation gave us mass to be big M. So okay, so after the collision, what's our momentum? After the collision, taking with respect to the fact that we are dealing with velocity, and here moving from left towards right is positive, and moving from left towards I'm moving from right towards left is negative. So in this case, we're going to have a negative velocity. Yeah, so we're going to have the mass times the velocity, which is negative, and this gives you negative or minus m times v, right? And it's moving towards the left direction, as you can see this way. So now what does it say? Is they say the total change in momentum of the body is, so as you can see here, is asking, what's the total change in momentum, and we need to find this out. So the change in momentum has the formula final momentum minus initial momentum. And if we know that it is final momentum minus initial momentum, so let's put out what we have from up here, like from above here, right? Like from above, we collect what we have and we slot it inside to substitute. So the change in momentum is equal to, so our final momentum was negative m times v, or you can say negative mv, and we have negative m times v minus initial momentum, which is m times v, right? Or we just have mv, and this is equal to negative 2 m times v or negative 2 mv. It all depends on you. As you can see in this situation here, inside here you have negative, like negative m times v minus negative, oh sorry, minus m times v. So you have this 2 m times v, and this acts like towards the left, right? So since that is negative, so the total change in momentum of the body is negative 2m times v. This m times v, you can just call it 2mv to the left, right? So it's sorry, the total change in momentum of the body is 2mv, right? Like 2mv to the left. This to the left shows that it is a negative sign that it's actually in front here, or the negative sign in front here shows that it is actually 2mv to the left. So okay, so that's the reason why our answer is A. Let's move now to the next question. Okay, so we are on our third question, and it says, which of the following statements about the motion of an object can never be true? A body speed can change without the body accelerating. Well, we don't know. B, a body can be accelerating while moving at constant speed. We don't know. A body can move as a result of constant resulting force acting on it. I think it's as a result of a constant resulting force acting on it. I don't know if this is actually correct. Please spare me the typos. I think this is how I actually collected the questions. Like, this is how the questions were. Okay, so D, a body's velocity can change at constant speed. Like, I think this is can change at constant speed. I think it's change at constant speed, not to change at. So sorry for that. A body's velocity can change at constant speed. Okay, so after your own turn, what do you think is the answer? Let's see. Okay, our answer is A. A body speed can change without the body accelerating. How come? Like, how? I mean, even like a body speed cannot change without the body accelerating. Simple, like, even if we can even take it to circular motion, right? Even if the speed is constant, the body still accelerates. Why? Because as it's moving around, the direction is changing, the velocity changes because the velocity works with direction, right? It works with magnitude and direction. So since it's one of its quantities, or sorry, one of its qualities, the direction changes. So it actually changes, and this change in velocity causes a change in acceleration, and acceleration too works with speed. So it's not like, as of now, I think it's not possible for a body to, I mean, to change the speed without accelerating. Then B, a body can be accelerating while moving at constant speed. Okay, so this can be seen in circular motion, right? As you can see, the body can be moving at constant speed, but because it's changing its direction, changing with velocity, so the velocity being changing causes a change in acceleration. Why C, a body can move as a result of constant resulting force acting on it. If you have this constant resulting force acting on the body, like let's just look at the movement of planets, you have this a resulting force acting on it, like, yeah. So this, and the force, I think, is constant and it's still moving, right? Yeah, unless it doesn't move if the resulting force acting on it is zero. That is now and in that case we say, okay, if that constant resulting force is actually a zero or a null force, like just zero, so the body just standing there. But as you can see, it's not really that making sense to be I mean, like he says, never be true. So I think it's it actually like maybe shows that aspect in all cases. I mean here it shows that in some cases, or like in a case where the resultant force is zero, it cannot move. But here it says never be true. Like, huh? Okay, so D, a body's velocity can change at constant speed. Mm, yeah, a body's velocity can change at constant speed. How? Circular motion again. As it's moving, the speed is constant, but the velocity changes. Why? Because you have this change in direction. Okay, so let's move to our next question. So our next question says, a snooker ball X moving with an initial velocity U makes an elastic head-on collision with an identical stationary ball Y. Hmm. Which of the sets of velocities below gives the velocities of X and Y after collision? So let's look at it again. A snooker ball X moving with an initial velocity U makes an elastic head-on collision with an identical stationary ball Y. Identical, right? Mean same mass. So, which of the sets of velocities below, that is the set of velocities here, gives the velocities of x and y after collision? So, let's see. For this, we'll take a different approach. We're going to solve it, and we can even bring up a story, and then we now show, okay, our answer is this, right? So let's move. Oh, yeah. Okay, so I have the story above here of this beautiful Christian holy damsel and this guy, holy girl. Like, okay, so this guy actually he loves the girl, and just the girl is just stationary. She's just like on her own, her God. Like she has the God. She's there, and this guy like he loves her, and he wants to come towards her, and what is driving him towards her is moving with a certain velocity, and it's that love. He's coming towards her like to ask her out. And so let's see how the storyline goes, and but the storyline is going to move with our solution to the problem. So in a perfectly elastic collision between two similar balls, the velocities of the balls after the collision can be determined using the principles of conservation of momentum and conservation of kinetic energy. So we're having these two principles that we're going to follow to have our two equations and resolve. You can even use the coefficient of restitution to solve your problems too. For me, so here the initial velocity of the first ball, which is the ball which is moving, is u, is our guy, and the initial velocity of the second ball, which is a stationary ball, or the stationary ball, is zero, the girl. It is stationary. Sorry, since it is stationary. After the collision, the velocities of the first and second balls are x and y respectively. X and y respectively. Let the sorry, I think I was supposed to write let their masses be m, since they are identical, right? It speaks about them being identical, like identical stationary balls. So they're identical, they have the same mass in this case. According to the conservation of momentum, which is one of the principles we are dealing with as in here, initial momentum is equal to the final momentum, right? The initial momentum is equal to the final momentum. I remember we're singing this song when we're like in third it. And here you see you have your, so what's the, from the previous, I think that was the third example. The second example, we saw that momentum is equal to the mass times the velocity. So the initial momentum will be the mass of each of these balls times their initial velocities. So for the first ball, which is the guy, his initial velocity is u, and you have his mass times u plus the initial velocity plus the mass of the second ball, which is tm, times the initial velocity, which is zero, and that m times zero gives us zero, and this is equal to the final momentum, which is the mass times the final velocity, right? Because here we can see that after the collision, the velocities of the first and second balls are x and y respectively. So for the final momentums, we are going to be taking their masses and multiplying by their final velocities to have a final momentum, right? I repeat, for our final momentum, we are going to have our mass times our final velocities. So in this case, we have the mass times x plus the mass times y, as we see here. So now, okay, let's move. So you see m is here, we see m here, we see m here, so we can just divide all through by m. So here divided by m, divided by m, divided by m, divided by m. U divided by m goes with m, and you have just u. 0 divided by m is 0. Yeah, we can just take that away. Mx divided by m is x, and my divided by m is y. So this is our first equation. Now let's move to see how we can come up with the second equation. And oh, I just left the lady alone this time. Wow. So let's see what the story says with the solving. According to the conservation of kinetic energy, initial kinetic energy equals final kinetic energy. Almost like the conservation of linear momentum. So here, the kinetic energy of the first snooker ball, like half mu squared, like from half mv squared, right? Half mu squared plus the kinetic energy of the stationary ball, which we know the ball it was stationary, so its velocity was 0. So like half m times its velocity, like 0, which just give us 0, and we are equating it to half m, the final velocity of the first ball, which is x, and we're squaring it, right? Plus half times the mass of the second ball and its final velocity, which is y. So dividing all through by half m, we have, so if I take here, I divide this by half m, divide this by half m, divide this by half m, divide this by half m. Half m is going to go away here, and we're just left with u squared, as you can see here. 0 divided by half m is like 0 again, right? We can just take that away. So half m x squared divided by half m, we have just our x squared, and here half my divided by half m, we just have just our y squared. So we have equation 2 here, and good. So we have just deduced our equation 2. Okay, now we have a system of two equations, equation 1 and equation 2, with two unknowns, x and y. We can solve these equations to find the velocities of the balls after collision, which is our unknowns, right? X and y. So we substitute equation 1 into equation 2. We're going to do the substitution like below here, but we want to see, like, we want to just do some little, can I say algebra here, and we'll see how it goes. Here we know that u squared is equals to x plus y squared, because what do we know? We know that our u from equation 1 is equals to x plus y. So we can now carry that u, since as here we have u squared, so we can just take that equation 1, which speaks of u being equals to x plus y, and we put it in the bracket and we square it, because that is the same as u squared. If u is x plus y, therefore u squared is the same as x plus y squared, right? So here, this is just the continuation. I have u squared, and I'm equating it to, I open this bracket, and opening this bracket, you know, for when you just have these two stuffs inside the bracket, you square this first guy, you have this, plus you take these two above here, you multiply by x and y, and you have plus 2xy, and then you square the second guy here, and you have y squared. So now, since this is a method to easily go about this, so since we know that u squared is equals to x squared plus y squared, and this is from equation 2, so what do we know? What do we know? We can take this x squared plus y squared, which is from our equation 2, and we equated, and equation 2 speaks about, I mean, this is it here, u squared is equals to x squared plus y squared, and then we take this and equate it to this our output we have from this algebra here that we solved from equation 1. So if we take this, our x squared plus y squared from equation 2, and we equate it to this our algebra that we finally had here from equation 1, because equation 2 speaks of x squared plus y squared being equals to u squared. So if u is equals to x plus y from equation 1, so when we put it here, we squared it and we had this output. So we can just take this guy and we equate it to the output we had when we slotted equation 1 inside here, and this is what we have below here. These are x squared plus y squared, and we're equating it to when we slotted x plus y inside this u and we squared it to have this guy. So this is it we have here. So if we simplify these, simplifying in the sense that we bring like terms together. As bringing like terms together, you see if you bring this other x squared, this other to the left, you have x squared minus x squared and it gives you 0. If you bring this other y squared to the left this way, you have y squared minus y squared here minus y squared, because when this y squared comes this way, it becomes negative. So we have y squared minus y squared and we have 0, and we're left with just 2xy. So that's what we're going to see in the next slide. And yeah, so let's see it. Okay, friends. So, oh, the boy is back. Let's see what will happen to him. Simplifying, we see that 0 is equals to 2xy. But how did this happen? From our previous slide, when we're below here, we saw that we had x squared plus y squared is equal to x squared plus 2xy plus y squared. And we saw that this x squared this way came this way, became negative x squared and went with this other x squared. And the other y squared this way came this way, became negative y squared and went with the other y squared this way. And so we're left with nothing, which is 0. And this way we're left only with 2xy. Okay, this has left us with two situations. This implies that either x is equal to 0 or y is equal to 0. But algebraically, we can see that, okay, there's a third situation where x and y are 0. But in this situation here, we are discussing physics of a body that was moving, and to come and it collided head on with a similar body. That means they had the same masses, like an identical body, and you don't expect the two of them to just like stand, right? So you don't expect the two of them to stand. So in that situation, we're not going to like consider the situation where you have x being 0 and y being 0, and it's not even among the answers, you can see. So I mean, this cannot even happen. I mean, like, so this implies that either x equals to 0 or y is equals to 0. Now let's see some explanation and how we can arrive at a final conclusion. In a perfectly elastic collision between a ball of mass m, that's the moving ball, and a stationary similar ball of mass m, the velocities of the balls after the collision will be as follows. Velocity of ball after collision, velocity of moving ball, right? The first ball after collision is x, and this is equal to 0. How? We're going to see why. And the velocity of the stationary ball after collision, which that velocity was represented, was like given to us as y, is equal to u. But why? How? In other words, the moving ball will come to a stop, to a complete stop. Velocity becomes 0 after the collision, while the initially stationary ball will acquire the velocity u of the moving ball before the collision, right? Of the moving ball, the ball that was moving before the collision, well, the stationary ball is going to acquire that its velocity, and it's going to move. So, right, and it's going to move. So this is due to the transfer of momentum and kinetic energy between the balls during collision. Here in my area, when we were kids, we used to play what we call billboards. I think that's the name in English. For us, we will speak pidgin English, we call it bize. So when we shoot this two, when the ball is coming and the other guy is standing and the other ball is standing, it comes and performs such a situation like this, and the one that was coming stops at certain periods, not all the time. It stops and the other guy continues. So we call that situation batam. Yeah, and we have a similar game to that. And when you have such a situation on your own turn, you take all the billboards inside the box, the box drawn on the sand or on the soil. And I mean, it's cool. Guys even play the thing when the rain is falling. I mean, guys were experts in it. So coming back to our story, we see here that, okay, the guy came, and when he came, like the two balls, and the first ball hit the second ball, the girl moved, and she was in a state of holiness and denied that she's going to serve God all her life as a single person. Maybe like a reverend sister, a focolarini. I mean, different, like you have different vocations. And she decides, and in life, when you have light and darkness,
When light comes, darkness goes away. So this guy came, and as he hit this girl, he gained Christ in him. He understood, and he decided to put Christ before. Maybe he might also decide to serve God alone in this, like as a single guy, like a priest or some other vocation, a monk, or maybe he might go and find a godly girl too, maybe who by God's will is also available for marriage. And if it's God's will for him to be married, everything we do by God's will. Okay, guys, so please, I have a message for you here. So let's see. So, friends, among these alternatives, which of them is the correct alternative? D. Interesting, right? Okay, so to conclude here on this story, we can see that love between a male and a female in the context of marriage is a beautiful thing. What's a beautiful thing God brought? And we say no to him. How is it pronounced? Homosexuality. And we also say no to fornication. As I said, in the context of marriage, God loves us all, friends. And I have a message for you. God, who is our Lord Jesus Christ, bless you. Amen. Goodbye. Love from Kombi. And guys, please don't forget to subscribe, like, share, and please comment for us to get to know more. And thank you very much. God bless you. Amen.